Good morning. At least it's morning here for me. I don't know what time it is for you when you're watching this, but it's a great day to be back with you guys teaching you. It actually invigorates me. It helps me with all this stuff being, without being at school. So hopefully this video finds you well. So we are going into, this is Module 7, Chapter 7. We're going to continue our study with functions. This set of functions that we're dealing with here, exponentials, is something that you've probably had a little bit of experience with, mostly in your algebra classes, maybe an introduction to these ideas. So I'm going to go over with you a little bit of the basics that go along with this. Grab your notepad, write down some of this information as we go. The stuff that you already know, obviously, then you can kind of gloss over that in your notes. The very first thing we need to look at is first of all, what is an exponential function? We're going to look at it in terms of its equation in its general form, and then the graph of it and how the function itself behaves. First and foremost, we have this, and you can see this up here, the general form of our equation being f of x equal to a times b to the x. We have a base value, that's the b value, being raised to our independent variable, the x value, to drive what is going on with an exponential growth function. Lots of applications to this situation. Anytime you hear like doubling, when let's say we have a population that's doubling, or we have half-life, that's something that's often talked about in science that maybe you've experienced. Those are actually exponential functions, one being growth and one being decay. Obviously, growth coming about, and we'll talk more about this in a little bit here, growth coming about because it's doubling. That makes sense. And then decay because it's halving, so it's taking half of an amount each time. So that idea, the doubling and the halving, that actually goes right back to this, what we call the growth factor, that b value, the base of the exponent. And then our a value is always going to be the initial amount, something that we start with. So in most problems, especially the ones that we apply, this maybe is a beginning population, that population being rabbits in the wild, or a certain amount of an element that is going to decay. So that is the initial amount. Also represents the y-intercept as far as the graph is concerned. So these are two very key points here, two very key values, obviously, that we want to track as we're working through these problems. Now, it's very important to understand that growth, actual growth, occurs when our b value is greater than 1. So anything that's greater than 1, it's like 1.3, 2, doubling, something's tripling. All these values are greater than 1, and it's going to create a graph that shows growth. It's going to create a situation that models growth. So in general, sorry about the squeaking there. My dogs are playing with the toy. I might have to kick them out here. Ash, no. So sorry about that. The basic graph of this, it's going to automatically have an asymptote. We'll show that here in a sec. That's the word that we have been looking at in our other functions. But it's going to have automatically an asymptote that is actually the x-axis. And it's going to follow along with our growth here. It's going to go from left to right. It's going to steadily, initially, increase in value. And then as we get further and further into our bigger numbers, think about that. The x value is our input amount. As x is increasing in value, that exponent is going to make our overall quantity as an output grow quickly as we get out further into bigger numbers. Think about it in terms of if I have 2 to the first power, well, that's 2. Well, as soon as I go 2 to the third power, it jumps up to 8. And you start getting into 2 to the 5th and 2 to the 6th. Those numbers start getting bigger and bigger and bigger. So quickly, you'll see that. So there is the basic form of an exponential graph. Now, you'll want to make note of, again, and I'm going to show this here on the graph, our y-intercept, that would actually represent the initial amount. So you can automatically know that A value is going to be, excuse me, I better do that right here. That A value is going to show up on the x-axis, I keep saying that, sorry, the y-axis. You can automatically know that 0A will automatically be on our graph. So that's our A value there, initial amount. So you can look at the graph and help, start looking at domain and range. What values can we put in for this function? What values can come out, or what values will come out, putting those values in. So hopefully you're getting to where in our study that you can look at any graph and start determining domain and range. You should be getting better and better at that as we're going here. So let's say our domain here, it represents, we're going to say it this way, all reals. So all real numbers. This is a good little review of how we can show this using interval notation. That means we can go all values from negative infinity all the way up to positive infinity. So there is our domain. Now our range is quite different. It's not going to just automatically, if you look at it, it's not just going to automatically be all reals. In fact, you can see that those output values are above the x-axis. So the question is, does it ever touch the x-axis? Well, you can mess with the numbers and you can start to see that. I mean, if you put, let's say that we have this growth factor of 2, we'll stay with this idea that the A value is 2. So if you raise 2, I don't know, let's put it way out there, to the negative 20th, remember, that's going to put it underneath 1. A negative exponent automatically puts our value below 1. So 2 to the 20th, 1 over 2 to the 20th, that's 1 over a very, very large number. So it's a very, very small because the big number's in the denominator. This ends up being 1 over 2 to the 20th. That's a huge number on the bottom, but it makes a very, very small number because it's underneath 1, very small decimal. So that graph is way out to the left is a very, very, very close to the x-axis, or very close to an output value of 0. So the range in this case is going to be all reals. I'm going to put an interval notation this time. So it's going to be all reals from 0. So a parentheses there because we're not including 0 up to positive infinity. So domain, range, and now the asymptote. Well, the asymptote's going to come about right there from your range. So the asymptote, you can see it in the graph. The asymptote is the x-axis. So we have an asymptote at y equal to 0. Remember, asymptotes are horizontal and vertical lines. In this case, we have an asymptote that is a horizontal, y equal to 0. All right, so we're going to continue in the analysis of these functions. So we also have in behavior. That is always part of our analysis of functions. So we're going to say it this way. As x goes to negative infinity, y, or f of x, is going to go to 0. It's going to settle on 0. Closer and closer. It'll never reach it, but it's going to get close to 0, way out to the left. And then our end behavior as we go to the right. So as x increases to positive infinity, our function y, or f of x, is going to also increase to positive infinity. So I would, encourage you to look at my example that I've given you here. Look on Desmos. We'll go ahead and pull it up right now. So if we get into Desmos, and that's 3 times 1.5 to the x, Desmos will confirm for us an example of what we just looked at. 1.5 being our growth factor, that's greater than 1. We should expect that this function indeed will take off to, so if we go 3, we're going to go times. And use parentheses here. You can use a time sign. I like using a parentheses when we're doing it on a Desmos or graphing it on a graphing calculator. And so we're going to raise that to the x, and you'll see indeed we get this increase quickly. You can go way out to the left and see as you go way out there, it looks like it's going to start touching the x-axis. But then if you zoom it in, you're going to see, you get way, way in there, you'll start to see this come up off the x-axis. We're clear out there at negative 39. And as we get smaller, or zoom in more and more and more, you're going to start to see, look at that. It's starting to come up off. It looks like it's touching the x-axis when we're way zoomed out. When we start zooming in, you can see that thing start coming up off and away from 0. Okay, and so if we set this back to home, we see then also that we have this y-intercept. So if we hover over the top of that, we're going to see that y-intercept is exactly 3 there, which is that initial amount in our function. Hey, good stuff here. We'll talk about exponential decay in the next one. We'll go quickly over that one and move along in this study. All right, guys, thank you very much for watching. We'll see how this goes.